I'd like to show you one more example, which is a little more advanced and ties together a lot of the recent concepts. And it's this one shown on the screen here, 12.3.5 from my notes. We've got a rod 12 centimeters in length, 1.5 kilograms in mass. There's 3 forces acting on it, and it's going to rotate about the axis shown by an X with a circle around it in the diagram. So first of all, it asks you to calculate the moment of inertia. And then second of all, it asks you to calculate the total net torque. So let's do it. All right, moment of inertia first. To calculate the moment of inertia here, the first thing I need to do is take a look at the size and shape of the object. The question says that this is a thin rod. The fact that it's a thin rod tells me what my starting point is for a moment of inertia. Namely, you want to go back to your table of moments of inertia, and you'll find that thin rod has moment of inertia 1/12 ml square. And if you feel like plugging the numbers in right away, m is 1.5, so we have 1.5 times the length is 12 centimeters, which is 0.12 squared, and then divide the whole thing by 12, and we get 0.0018 kilogram meter square. But we're not done yet. That is not the answer, because that is only the moment of inertia if the rod were rotating about its center. So now we need to take a look. Is the rod actually rotating about its center? So this one is marked with tick marks. So we have 1, 2, 3, 4, 5, 6 sections of the rod. So the center of the rod is here. That's the center of mass, because it has 3 sections to the left and 3 sections to the right. So that's the geometrical center, and presumably it's a uniform rod, so we expect the center of mass to be in the middle. But the actual axis of rotation is over here, which means we do have a parallel axis theorem case here, and we need to figure out the value of D. So remember that D goes from the center of mass to the new axis of rotation. So it's 2 segments of the rod. It's a 12 centimeter rod, and there's 6 segments. So each one of these segments is 2 centimeters, which means D equals 4 centimeters. So now we have an MD square term to add to this. So it's going to be 1.5 kilograms times 0.04 squared. And that gives me 0.0024 kilogram meter square. And now the total moment of inertia of the rod, which sometimes I call IP, the moment of inertia about the parallel axis, would be the sum of these two things, ICM plus MD square. So that's going to be 24 plus 18 is 42. So 0.0042 kilogram meter square. So that's the actual moment of inertia of the rod. So question 1 completed. There's your moment of inertia. Okay, let me clean up the picture a little bit here and move on to question number 2. For this one, we want to know the total net torque on the rod. So we've got 3 forces acting on the rod. That means there's going to be 3 torques as well. Those torques are going to be signed positive and negative based on which direction they go in, and then we add them all up to get the total net torque on the rod. So I'm going to think about this using the force component based idea of how to calculate torques. So my thought process is I'm thinking about each torque as being FTL. So let's just go through them one by one. Let's call this torque 1, and this will be number 2, and this will be number 3. Okay. Okay. For number one, let me try to do this step by step to be as careful as I can be. First, I want to draw a circle which represents visualizing the rotation of this thing. And that circle is going to look like this. Again, the key properties of that circle is the center of the circle is the axis of rotation, yes, and it needs to touch where the force is acting on the object. So this is actually going to be the circle that applies to force 1 and force 2 because they're the same distance away from the axis of rotation. You'll also notice force 1 and force 2 are both already tangent to that circle. They both are right along the tangent lines to the circle. So that means we can actually skip some steps here. We don't actually have to take any force components. Ft is just equal to the entire force for number 1 and number 2. Again, that's because the forces are already tangent to that circle. So the only thing we need to make note of is what's the value of L. So L, remember, is this distance here from the axis to where the force is acting, L, and that's going to be, for this case, L equals 2 centimeters. Because remember, each one of these little segments is 2 centimeters. And so for the first torque, we're going to have tau 1 equals, Ft is 4 newtons, and L is 2 centimeters, 0.02 meters. And I need to double check, should that be positive or negative? So looking just at force number 1, would that cause a clockwise rotation or a counterclockwise rotation of the rod if that was the only force acting on it? And the answer is it would cause a counterclockwise rotation because force 1 is pulling it in that direction, which would be, you know, this way, counterclockwise. So that means this is a positive torque. Okay. For torque number 2, we can recycle most of the same work because it's the same circle, it's the same value of L, it's the same force magnitude even, and the force is still tangential. So this is also going to be the same value, 4 times 0.02. And this one, let's check if it's positive or negative. F1 points up and F2 points down, but actually the torque is still positive. Because if you look at F2, F2 is making it rotate in this direction, but that's the same direction as this direction because you could form a circle like that. Both of those forces are causing it to rotate counterclockwise. And this is something that people commonly mess up in this section. Just take careful note that the forces are not in the same direction there. And in fact, you know, F1 is pointing in the positive y direction. F2 is pointing in the negative y direction. So the force components have opposite signs, but the torque is still in the same direction because it doesn't matter up, down, left, right here. It only matters clockwise versus counterclockwise. And both of those are inducing counterclockwise rotations of the rod. So anyways, torque 1 is positive 0.08 Newton meter. Torque 2 is positive 0.08 Newton meter. Now let's move on to torque 3. So let me erase this stuff because I'm going to need to redraw all that. I'm going to need a new circle for torque number 3. It's going to be a bigger circle. This one might be a little bit tough to draw. Let's see how close I got. That's not too bad. Right, so I'm going to visualize a circle like that. Again, I want the axis to be at the center of the circle, and I want force vector F3 here. Force vector F3 here to be touching the edge of the circle. Now, next, I think about this arm that goes out to where the force is acting like this. That's going to be my L value. This is going to be 246 centimeters in this case. So that's 6 centimeter. For this one, I do have to worry about the force components because I can see this force is not tangential. This force has a tangential component, but there's more to it than that. So let's be a little bit careful. Let's switch colors here. What I want to do is visualize a tangent to the circle like that and drop a perpendicular like that. And then I have a right triangle here that I can solve. And that right triangle, let me just redraw it off to the side here. So that right triangle, it looks like this. The right angle is up here. The hypotenuse is 6 newtons because that's the magnitude of the force. I have the exterior angle to the triangle is 65, which means this angle here is 65 by alternate interior angles. So then the component I want is going to be this side here, the one that's parallel to the tangent. So I'm going to have Ft equals 6 times sine of 65. So that's going to be 65 sine times 6, and that gives me 5.44 newtons. By the way, instead of sine 65, you could do cosine of 25. That would also be fine if you drew the triangle a little bit differently. So I've got a value here. L is 6 centimeters. Ft is 5.44. So that makes the torque equal to, torque 3 equal to 5.44 times 0.06. And I need to check if this one's positive or negative. So let me look back at the force again. Ask yourself, if this was the only force acting on the object, which way would it rotate? And the answer is it would rotate that way because it's pulling up on the left side. And that is a clockwise rotation because it's rotating around this way now, which is the opposite of what it was doing before. So this torque is actually negative. So tau 3 is negative. Now, if I crunch the numbers on that, 5.44 times 0.06, I got 0.326 Newton meter, and that's negative. So then finally, I want the total net torque on the object. So that's simply going to be the sum of the 3 individual torques. So the total net torque, I'm kind of out of space here. Let me do it up at the top. The total net torque is going to be 0.08 plus another 0.08 minus 0.326. So that's going to be negative, let's get rid of that, negative 0.166 Newton meter. So there's my torque. So the fact that the total net torque is negative tells me that ultimately the change in this rod's motion is going to be in the clockwise direction. So if I release it from rest, it'll start moving clockwise. And the total strength of that torque that's rotating it clockwise would be that number here. And we'll learn very shortly how to actually determine the rod's motion based on that information.